couple things. And just so that you guys are aware, I've left out differential equations, which would have come up under Newton's laws. You don't have to have it. It's not on it's not on the semester exam, so I'm not too worried about it. But we will have to cover differential equations. It comes up a bunch of times, and we'll see it. But I normally would have covered it, and we would have done a lab on it. And that's going to be the coffee filter lab. And we will have to do that lab, and I'll work it in, but I'm not sure when I'm going to work it in. It might be second semester. The other thing that we've left out, I said, is Hooke's law, which is the force that we get from springs. It's just a tension or a normal force, depending on how the spring is used. But springs deform. They stretch or they compress. So we have to learn about that compression. So we will work that in when we talk about work, energy, and power, because it comes up during work and energy. But the thing about this discussion is that work is going to represent some of the first mathematics that involves calculus and symbology from calculus. So that's going to be unique to a lot of you who don't have calculus this year. It's not particularly hard. You've already done the work that you need to do for the symbology we have. You've done an antiderivative before. And because of that, you know kind of what's going to happen here. I just have to put all the symbols with it, because on your equation sheet, the definition of work is an integral. Now, we're going to talk about what this is next week, and I'm not really going to go into it today, but your equation sheet has it, and because of that, it's appropriate that you see it and what it's going to look like and what it means for us. There's a lot of symbology here, and what I mean by that is almost everything here has some kind of importance, and it's difficult to know what that importance is. For example, work is a scalar. Notice no bar on it. Force and displacement, which is what those two things are vectors. And there's a special kind of multiplication between them called a scalar product. It's a type of product that takes two vectors and produces a scalar, sometimes called the dot product. So you might think that that's supposed to be multiplication, but it's a special kind of multiplication. And then this is the integral symbol. So all of this has meaning, but for the time being, we're going to approach this without calculus. And the way this looks without calculus is a little bit easier. Force times distance times the angle between them. Cosine of the angle between them. Now, equations don't tell us very much. So I want to talk about work and energy today. I'm not going to talk about power, but work and energy and what they mean. I said from the beginning of our unit on force that force represents the absolute most difficult way to solve a problem. It can solve any problem. Now, when I say it can solve any problem, all of the problems we saw had constant forces acting on them. I know you might think they were complicated. That's not how the world works. The real world, the forces are changing all the time. Even if you're just driving your car, the angle of the roadway in your car is constantly changing. The force of the wind on the car is constantly changing. The pressure you apply to the gas pedal is constantly changing. All sorts of dynamics are changing all of the time. Actually trying to predict what the car is going to do is nearly impossible. And that doesn't even begin to describe the hard stuff like walking. Do you know how hard it is to make a robot walk? It's because walking is hard. What you do naturally is difficult to explain. All those forces everywhere in the body are all changing in a very dramatic way all the time. All we did is deal with a couple, three forces acting at a constant on an object. But if you want to go from here to Mars, the force of the Earth's gravity on your spaceship is always changing. And then you have to apply the force of the sun on your object and the force of all the other objects around it. And they all change with distance. These are force problems that are really hard. They don't have solutions. Instead, we have a computer kind of tell us the size of the force and give us information about how that force might be changing. But we can't come up with an equation for an answer like we have in this class so far. Force represents the absolute most difficult way to analyze a problem. But it gets us places. Everything else we're going to learn is about how to get around using force, about another method, something else that could potentially not have us look at the forces on an object. And our first example is work. Now, work has a broader meaning, and I want you to understand the meaning and its importance and position in a study of physics. But also, solving problems is a lot easier using work than using forces. If you can use work to solve your problem, you always should. It's faster, it's more direct, and yields very, very good answers. So when you're looking at a problem and trying to figure out whether you should use forces or you should use work, one of the number one things you should look for is velocity. Are they interested in the velocity? Because work energy problems are very good at dealing with velocity. They're also very good at dealing with displacement. And if done correctly, you'll never need to know the acceleration of a system. See, the goal of a work energy problem is to give you the results of applying a force, but not having to know what the force was actually doing. That's really the goal of using work, is it tells you what happens at the end. I care about the object going down a slide. I don't care about its time on the slide. I just care about how fast it's going at the bottom. That's a work energy problem. Yeah, you can use forces, but work energy is a lot easier. Work energy tends to combine everything we do with kinematics with everything we do with forces and just give you the change in velocity, give you how far it went. That's what it will be about. Now, there's something broader about work you need to know. And there are several things about it that I'm going to point out, but this is the definition I want you to know. Work is the method Work is the method by which you change the energy of a system. Work is the method by which you change the energy of a system. I have to use the word system here because work is a broad topic. You can do work a lot of different ways. But in every instance, the energy of a system is changed by the work you do. Now, you have to understand the vocabulary here. I will say that you do work on a system. Meaning the way I use the word work is like I just used it in the sentence. A force does work. You do work. You can lift something up and you are doing work. The act of doing work is the act of changing something's energy. So there is positive work and there's negative work. When you do positive work, you increase a system's energy. As opposed to negative work, which will decrease a system's energy. Work isn't a vector. So I spent the entire semester trying to train you that positive and negative is about direction. But work is a scalar. So positive and negative isn't about direction for work. It's about increasing and decreasing, just like you were trained back in primary school. So in this case, your definition of positive and negative fits in because work isn't a vector. Now, you do have to understand that the conduit, the way energy is transferred, is through a force. It is a force that connects you to the object that allows you to give the object energy. So work is done due to an applied force. I probably should write that whole thing. Work requires an applied force in the direction of motion. Now, in the direction of motion doesn't mean the direction it's moving, but along that direction will determine whether work is done. For example, if I throw a baseball, I apply a force to the ball and change its energy. I have done positive work on the ball. The ball now has more velocity than it had when I was just holding it. I pushed on the ball in the direction it was going, so I applied a force to the ball that changed its position while I threw it. Then it left my hand. Now, that whole time, the ball also did work on me. It pushed on my hand, and it pushed my hand in opposition to the direction it was going. So I did positive work on the ball, but the ball did negative work on me. I lost energy and gave it to the ball, which increased its energy. Work connects objects together. When I do work, I can take energy I have and give it to something else. So when I do positive work on an object, by Newton's third law, something else is having negative work done on it. You guys understand that? So for every instance of there being positive work, somewhere else in the universe is an instance of negative work also being done. Now let's say you catch the ball. If you're the one catching the ball pushes on your hand in the direction your hand is moving. The ball does positive work on you, giving you more energy. But you do negative work on the ball because you're taking energy away from the ball. Now, unfortunately, the energy you acquire from the ball probably isn't very useful. It probably made noise. It probably made the glove hotter. It's probably not actually energy you're going to get back and use later that day. Not all forms of energy can be recuperated. So be aware that just because I say you gained energy doesn't mean that was useful energy. Now, in all of this, you've heard me talk a lot about velocity. And you talked a little bit about energy. It's hard to understand energy from a standpoint of a macroscopic view of the universe. But at the most basic level, energy is motion. The most basic form of energy is motion. If you do positive work on something, it's likely moving faster. And if you do negative work on something, it's probably moving slower. Does everyone understand? So if you do positive work on something, you are increasing its energy. If you do negative work on something, you're decreasing it, which means you're probably making it go faster. But also, anytime you see an object go faster, something did work on it, every time. So anytime you see an object go slower, something did work on it. So you can literally tell if work has been done by looking at a change in velocity. Any change in velocity means work has been done on your object. It's the easiest way to tell if work's been done, is by just looking for a change in velocity.